So, welcome to the second lecture in this two-lecture series on the Linux operating system. So, we'll start with memory management. So, the physical memory management system of Linux, it deals with basically managing system memory, which also would include managing virtual memory. That includes allocating and freeing virtual pages, creating groups of pages, dealing with small blocks of memory, huge pages, and so on. Furthermore, we will also look into ways of creating shared memory segments between, let's say, two processes, such that just by writing to their virtual address space or their respective virtual address spaces, and a degree of inter-process communication or IPC can be achieved. So, from the point of view of the kernel, so it does deal with physical memory, even though using the virtual abstraction is still preferable for large parts of the kernel. So the kernel has its own virtual memory. But still, large parts of the kernel also deal with physical memory because they need to work directly with it. So traditionally, as per on the x86 architecture, the physical memory has been split into different zones, and the different zones are used for different tasks. So the first zone is known as the DMA zone, which is typically the first 16 megabytes. And these sizes keep on changing with the kernel version. So this is mainly for DMA operations where where it is assumed that the DMA controllers will directly write into this zone. Then there is a normal zone where we look at regular applications, and then a high mem zone. So as I said, with different kernels, the sizes of these zones and these connotations change. But what is important to bear in mind that the physical memory space itself is zoned for different kind of tasks. So the most important being normal applications as well as DMA kind of tasks, which the DMA controllers will only access. So now the key question is, how do we manage physical memory? So for managing virtual memory, we had the page table and the TLB and so on. But managing physical memory is different. I won't say it is difficult, but it is different. So the page allocator will of course manage all the physical pages, but sometimes we will be given a big chunk of physical memory which needs to be managed differently, not using the traditional page allocator. So it will be given a set of physically contiguous pages, and then we will have to keep our kernel data structures over there. So this will not be in the virtual memory system, which means that we need to have separate or special allocators for physical memory. So one of them, so there are we'll look at two algorithms. One is the buddy heap algorithm, and we also look at something called a slab allocator. So what happens is that we create memory regions where each memory region is paired with an adjacent partner of the same size. So what happens is that in the memory, if let's say one 4 KB chunk and another 4 KB chunk, both of them become free. So what we do is that we combine them and create one 8 KB chunk. All right. So this is what it means, that whenever two allocated partner regions are both freed up and they are consecutive, they are combined to a larger region. Furthermore, what happens is that if let's say there is a small memory request which cannot be satisfied by allocating a small free region, then we'll take a larger free region and subdivide it into two partners. So let's give an example. Let's say that there is a 4 KB space, right? So this entire thing is 4 KB. And let's say I want 1.5 KB. So given the fact that now we are not dealing with virtual memory, right? So we are dealing with the raw memory itself. And I don't have a 1.5 KB sized hole in my physical address space. So what I will then do is I will split this region into two parts, 2 KB and 2 KB, where this 2 KB is free and this 2 KB will be given to this request. So it will basically use 1.5 KB and zero point 0.5 KB will be free or wasted. So if you can think about it, we are essentially creating a tree. Okay, so that is the key aim over here. where a tree is being created, where we have a large region. Again, we divide it into two parts. So one part could be free and one part could be allocated. Again, we divide that into two parts. So it need not be a complete tree, right, or a balanced tree. But we'll essentially have free parts and allocated parts. So this is known as a buddy allocator, which is reasonably effective in managing large chunks of physical memory because, as you can see, it reduces the wastage. So the memory allocations in the Linux kernel can happen statically in the sense a driver would ask for a continuous memory region, let's say at boot time or at the loading time. Or we could have the page allocator for a kernel. So for the kernel memory, we can also use the slab allocator, which we will discuss. And furthermore, the page cache and parts of the VM system, they also reside in physical memory. In the sense the page table cannot be stored in virtual memory, right? So then that will become a recursive data structure. So the page cache is the kernel's main cache for uh, uh, so, so so basically let me differentiate between a page cache and a page table. So a page table is the one that contains the traditional virtual address to physical address mapping, and this has to be stored in the main memory. It cannot be stored on virtual memory. And the page cache is something where is the kernel's main cache for files and IO. So if you would look at a traditional IO system and we want to read a file, then before going to the disk, we see if, let's say, for that disk address, if we have something in our cache. If you have the same data in our cache, then we can access it from main memory, which is much faster. So the page cache also has to be there in physical memory, kind of unvirtualized. And the same holds true for the page table as well. And the page cache in this case would store, the file contents for local devices or network file IO or something. In fact, there are a bunch of kernel data structures, which of course includes the page table. It includes the page cache, which cannot be accessed via virtual memory. They have to be accessed directly. In a sense, we need dedicated kernel level physical address space memory managers. The buddy allocator was one such memory manager where we give the buddy allocator a large region and it keeps dividing them in half, right? And each half it again keeps dividing. So it'll have many of these small chunks and it'll have, then it'll divide this into this and maybe it'll divide this and this. So it's possible that, this part is occupied and, this part is free. And so this is typically what the buddy allocator does is that it will create a tree of these blocks. Some will be occupied, some will be free, but at every level we'll essentially have a block and we'll have a pair, right? So that's the typical idea that whenever we break it into halves. So the buddy idea is one idea in this space, but we can have more ideas or different ideas. So the idea of the buddy was that we take a 16 KB region, divide it into two 8 KB regions, and let's say our request is a 4 KB. Well, then we again divide 8 KB into two parts, 4 and 4, and maybe this part we use and this part we don't use. The other option for actually storing kernel level data is to use a slab memory allocator. The aim over here is to reduce some of the internal fragmentation that was happening in the buddy allocator. So we can have a bunch of kernel objects, right? So they could be files for file system objects, and they could be specialized entries for networking objects or for process control and so on. So it doesn't matter. So basically, the only thing that matters for a slab allocator is the size of the object. In this case, if we are talking of 3 KB kernel objects, the critical structure here is a cache where we have a separate cache for a separate object type. So what the caches actually have is that they have these slabs. So the key idea of a slab is that here we keep, so in every cache over here, what we have is that we have these chunks of these objects. And so each object, let's say, has a size of 3 KB. And basically, a cache stores a pointer to each of these objects in a physically contiguous page. All right. So then what happens is a physically contiguous page is broken to. So a slab in this case basically refers to a set of chunks where each chunk is large enough to store a 3 KB object. So what happens is that let's say for any object type, so let's say the 3 KB object type, we define a bunch of slabs in a memory region which is reserved for only storing that object type. So this is essentially a set of contiguous pages. So what is the size of a slab? Well, that could be the same as a page size, a multiple of a page size or less than it. So that really, it's not important to specify that. So a slab is basically a continuous region of memory within the large memory chunk that has been allocated for this object type. And within a slab, of course, we have these 3 KB objects. So for a cache, which is a second layer, which we have not discussed up till now. So basically a cache contains a single directory, let's say for a slab, and we can always increase the size of this cache, but the increase will only be, for in a slab wise fashion. So a cache will basically refer to an integral number of slabs. So what a cache basically does is that it stores pointers. In the sense, it stores a pointer to the entry in the corresponding slab, right? And furthermore, it says whether the entry is full or empty. So this is primarily the main information that the cache stores, whether it's full or empty. So the next time that, let's say, we need a 3 KB object, we will actually go to its cache. We'll find a slab which is partially full, right? Not empty, but partially full. For example, this white entry is partially full. So this entry will be allocated for the object. Similarly, we could have a bunch of slabs for 7 KB objects. And as you can see, both the slabs, this one and this one, they are partially full. So the next time that a request comes for a 7 KB object, we may want to allocate this entry because this will fill the slab, right? And then, no more entry can be allocated here, which means that this will remain in the cache, but this part of the cache need not be queried anymore. This will simplify things. So the cache basically acts as a directory into the set of slabs which are stored in memory. But if you would see here, there is much little space wastage as compared to the buddy algorithm because we take a large chunk of space, divide it into slabs, and then we divide the slabs into objects where the entire aim is to minimize the wastage. And the cache is required to basically it acts as a metadata for the slabs to indicate which entries in a slab are empty and which ones are full. So now coming to the virtual memory or the VM subsystem, it maintains the address space of each process. Its job is to create virtual memory pages on demand. So you may want to look at the BRK system call, which increases the virtual address space of a process. It manages the loading of pages from disk and also swapping back. It interacts with the swap space. Furthermore, the VM manager maintains two separate views of a process's address space, which are namely the logical view and the physical view. So, logical view describes the layout of the address space, where the address space will, of course, consist of a set of non overlapping regions, and each will be continuous and page aligned. In the sense, logical view contains the text of the process, which is basically the code of the process, the heap, and the stack, and so on. So, that is like the memory map of the process. And then, of course, there is the physical view of the address space, which is stored in the page tables, which does nothing but the virtual to physical address translation. So, in the case of virtual memory, let us look at some of the important concepts. So, one is that we will have something called a backing store. So, backing store basically means where exactly the pages are coming from, right? So basically, it is possible that the pages are not coming from anywhere, in the sense that if you consider the main memory and there is a region in the main memory, that just that part of the region or that frame is just mapped to a page, right? So in that case, this is like demand zero memory, in the sense whatever you see on the main memory, that is the data. Alternatively, what could be happening in a virtual memory system is that, let's say, a part of the virtual address space may be mapped to a file. In the sense, anything that I read, you are actually reading it from the page cache, but the data is there in a file. And if you're writing to a region, which is nothing but a region in the page cache, the writes are being reflected in the file. So in this case, the file is the backing store, right? So in this case, virtual memory has a deeper connotation, which basically means that if any write is made to virtual memory, it needs to get reflected in the backing store. In the sense, if this is the virtual memory and some write is made to it, it needs to get reflected in the backing store. All right, that's the idea. So furthermore, we can implement the copy on write paradigm. So the copy on write paradigm could be that when we are forking a process, for instance, we will have two processes, P1 and P2. When we fork them, the memory space gets replicated, but we don't have to replicate it immediately. We will just map the same physical frame to the virtual addresses of both. But the moment there is a write, that is when we'll create a separate copy and then we will separate them. This is a standard copy on write mechanism which we have seen earlier. And this, of course, is done in response to a fork system call. But the kernel can also create a new address space with a new program when we are executing the exec system call. So at that point of time, when the exec system call is executed, so then of course a new memory map is created corresponding to the code of the new program. So on executing the new program, where the keyword or the operative word being new over here, an empty virtual address space is created where the program loading routines will load the address space and the virtual memory regions as per the directives embedded in a new program. However, if we use fork, then the idea is to create a complete copy of the existing process's virtual address space. But again, as we have discussed, it is not done immediately. A copy on write mechanism is used. So what is actually copied is the VMA descriptors or the metadata is copied. A set of new page tables are created for the child, which basically means that while initializing at the time of the fork system call, the parent's page tables are copied directly into the child's, right? And the reference count of each page that is covered is incremented. After the fork, the parent and child they share the same physical pages, right, in their address spaces. That is exactly why we increment the reference count, because previously only the parent was referencing it. Now the parent and the child both reference it, right? And then, of course, there is a copy on write mechanism that if any process writes to the page, then a new copy is created and a separate mapping is also created in the page table. So coming to swapping and paging, so the VM paging system will essentially relocate pages of memory from the physical memory to the disk when of course the memory is needed for something else and we do not have adequate space. So that is when, as we have studied earlier, frames go from memory into the swap space. So there are two main mechanisms, the page out policy. So this algorithm will decide which pages to write out to a disk, and this will of course depend on a priority mechanism of processes and their data and so on. Then there is the actuating mechanism known as the paging mechanism, which is going to actually carry out the transfer, right? So it will then uh, carry out the transfer in the sense between the main memory and the swap space. It will either write it into the swap space or bring the data back depending upon the direction. So it can swap to other kinds of devices as well. It's just not limited to the hard drive. And furthermore, so we will have two, bit vectors or bit maps, as you may call, where the job of the bitmap is basically to store for every single frame is it occupied or not, 0 or 1. And for the swap space also we'll have a similar bitmap that every single frame in the swap space is it occupied or not, 0 or 1. So this is how we can track which frames are being used and which frames are not being used. If we want to allocate a large sequence of contiguous memory, as we have seen for the buddy allocator or the slab allocator, then of course we will have to find holes in this bitmap, right? Sequence of continuous zeros. In the sequence of continuous zeros, it's possible we may find multiple holes, but to reduce fragmentation, what we would like to do is that we will choose the next fit algorithm, which is the hole that is just about larger than the memory that is requested. With regards to kernel level virtual memory, so what the kernel typically does is that it reserves a part of the virtual memory for its own work. So traditionally what used to happen with 32-bit systems where the total virtual memory was 4 GB, that 3 GB was for user applications and 1 GB was for the kernel. So with 64 GB, of course, we have different splits. So now a valid question could be that why can't the user and the kernel just share the same virtual address region at least? Well, the idea is very simple that when we switch from user mode to kernel mode, we would not really like to flush our TLBs, right? Because flushing the TLBs, etc., is quite expensive. So if you want to keep the same TLB mapping, then we basically uh, need to differentiate on the basis of the virtual address. And that is easily done if the kernel level virtual addresses are in a different zone. Similarly, when we swap back from the kernel to the user, we will again not like to change the page tables. And the user cannot access kernel level pages anyway because the built in privilege level bit will basically be in the user mode, right? And then a small circuit will see that look, you're in the user mode, but you're trying to access a kernel level page, which is not allowed, right? And whether a page belongs to a kernel or not is easily figured out on the basis of its virtual address. So that is why it makes a lot of sense to actually split the virtual address space. So the virtual memory area of the kernel contains two regions. One is a static area, uh, where it contains, you have page table references to the entire available physical memory of the system, right? And basically there is a translation from physical to virtual addresses while you are running the kernel code. Okay, so basically in this case, what happens is that essentially the mapping between virtual and physical addresses is fixed. So we take some of the key data structures of the kernel, like as we have seen page cache and page table and so on. So they can still use the paging mechanism, but it is just that the regions, their physical addresses, and the mapping is fixed. So this ensures that the same kernel code, you will work and nothing will change. And so the kind of guarantees that we needed, these issues of who pages the page table and what if chunks of the page table are swapped out and so on. Those issues are, we don't have to deal with them. And that is because it's a fixed mapping. But as I said, not the entire part of the kernel does not have to be in the regime of this fixed mapping. So then, of course, there could be most of the kernel could be under a dynamic virtual memory mapping kind of system where the section is not reserved for any specific purpose. So the page table entries, etc., can be modified, where a given virtual address over the course of execution can be mapped to multiple physical addresses, as is the case with normal programs. So normal programs only care about the virtual address and not what it is mapped to, which gives us a degree of flexibility in the sense we can swap it out. If it's mapped to PA1, we can swap it out and again bring it back to PA2. So for the dynamic area, this behavior will be possible, but not for the static area. So these pages are typically pinned in memory, and furthermore, the mapping is also fixed. This ensures that the critical data structures of the kernel remain correct. Now we will discuss executing and loading user programs. So Linux maintains a table of functions whose job is to try to load programs. So essentially what can happen is that we can have a bunch of binary programs, not one, but we can have, several binary programs in several different formats. So ELF is one of the more popular formats. So whenever a program is presented to the operating system to basically run it, so the first sub program within the kernel, sorry, within the, so a lot of this runs in the user space, but a lot of it also runs in the kernel space. So let's say within the kernel, in the user plus kernel, the program that actually looks at it is the loader. So the loader tries to parse the format of the binary. So of course there are multiple functions and multiple functions try to parse the format of the binary or parse the binary. So whichever one could successfully do it, it then tries to load the program, which basically means extract the code pages, map them to virtual memory, extract all the constants, map them into virtual memory, and create the virtual memory regions for the stack and the heap and so on. And in many cases, particularly when we are randomizing the addresses, right? So when we have ASLR, address space randomization, some memory locations for the start of the stack and heap and so on have to be also populated by the loader. All right. So the point is the mapping is made, but it is not really necessary to bring the page or the data into main memory, even though sometimes it may be necessary to do so. So when it is necessary to do so, then we would prefetch the pages. But in general, what would happen is we will execute the program, and then when it will start executing, we'll have page faults. The moment we have page faults, the data will be loaded from the disk into physical memory. So the ELF format binary file, which is by far the most popular, consists of several sections. The sections are aligned to pages. So we would never have that the text section kind of straddles, ends, but ends by straddling two pages. In the sense, this is one page and one page, and the text section is still this point. That's not going to happen. So the ELF loader will essentially work by reading the header, mapping the sections of the file to regions of virtual memory, and essentially populating registers, if that is the convention, with addresses like the start of the stack and start of the heap and so on, and then letting the program execute. So as the program executes, it will not find its data in main memory. We'll have page faults, and that's when we will, in a demand paging kind of fashion, page in the pages. We could also have prefetching, where you kind of guess the pages that the program will access, and those pages are brought into main memory at the beginning, such that once the program starts running, you at least minimize the page faults or reduce the page faults at the beginning. So the typical layout for an ELF program in virtual memory would look like this. So first note the separation between the user space and the kernel space. So this is the user space and this is the kernel space. So this part of the memory or the virtual address space is invisible to the user code. So the user code will start over here with a downward growing stack. Then we will have our memory mapped regions which can grow upward. And then we will have So these memory mapped regions over here are essentially for some DLLs and also for when we memory map files, right? And then again, let's say if we start at address 0, the first few bytes store header information for the ELF program or the ELF binary. So they contain some fields. So some of them I can mention. So one of them is a magic number. So the magic number essentially identifies the format and also the version of the format. So there's many. There is also much more metadata. So the metadata talks about the sizes of these regions, their starting points, and so on. So all this information is there in the header of the file. So this is known as a forbidden region. And then we have the text of the program, which is nothing but the code. We have the data section for global variables where the data is initialized. Then we have a memory region for uninitialized data. So in this case, nothing needs to be done, but we just need to allocate space for it. And how much space to allocate, this is there in the header of the binary, which is there over here at the beginning. So the most important section for the from the point of view of dynamically allocated data structures is actually this section for runtime data. It's also known as the heap section. So the heap grows upwards. So clearly this diagram is not drawn to scale in the sense, these voids are actually huge. But the heap section is where all the dynamically allocated data from the malloc and the new system calls, all of this data is allocated. So it's allocated over here. So what the OS dynamically maintains is the BRK pointer, which is essentially the pointer of the topmost address of the heap. So with the BRK system call, this pointer can increase, which means the size of the heap will increase. So now let's come to static and dynamic linking. So typically a program in Linux, any program, let it be a.out. We can at the shell run the command ldd a.out. This will basically tell us what all are the libraries that need to be linked with the program at runtime. So we always have the option of static linking, which is that we take the program, we take all the functions from static libraries and add all of them, and we make a large binary. So the problem with this is we'll end up linking so many functions that the binary will actually become very large. But at runtime, we may not actually use that many functions. In fact, we may actually need a few. So the main disadvantage of static linkage will then be that we will just have copies of functions which are anyway there in system library files, and we'll just have tens or hundreds of copies which will take up space in our memory, take up space in our disk with no apparent advantage, actually, not apparent advantage. That is why it is much better that we have pointers to functions, but we don't embed the code of the functions, and this is done within the scope of DLLs or dynamically linked libraries. So dynamic linking is quite efficient in terms of both memory space, memory usage, and disk space usage. So what it does is that, let's say if a given function is dynamically linked, the first time you call it, it actually goes into one dummy function. And so the dummy function, what that does is basically it realizes that, look, the function has not been loaded. It locates the dynamically linked library, makes a few system calls. The system calls then place the code of this in the memory map of the process. And then a pointer to the actual foo function is returned, and this is stored in the stub function. And then, of course, the real foo function is called. So the next time we call function foo, again it gets redirected to the dummy function, which this time does not reload the DLL or doesn't load the DLL because the function real foo has actually been loaded. It's now in the address space of the program. So all that it will do is it will just pass the arguments to the real foo function and then get the results out. That's all that it will do. So this is a fairly simple way of doing it, that we can use these libraries to reduce the size of our binaries and to also ensure that there is some degree of consistency in the sense that everybody is using the same system libraries across systems. So I can just send a binary across. It will then use libraries from the local system and run. So this will also reduce the size of the binary files. So Linux has a special linker library to implement dynamic linking. So they are called DLLs, but they are in Windows, but on Linux they are known as SO files or dot shared object files, which is quite easy to do. You can also using GCC, you can have it's quite easy to compile an object file to be a shared object. So you need to supply a few more flags. So one flag is minus f pick. So pick basically means position independent code, and f is an option. So basically this tells GCC that look, so GCC is the C compiler on Linux that generate position in independent code and also create a shared library out of it. So these are the flags that you need to do, and minus C is create an object file, right? So in this case, if it's C shared, it creates a shared object file. So different GCC versions will have slightly differing values of these options, but it's always good to look up the documentation before generating a shared object file. And once a shared object file has been generated, it can then be distributed as a DLL, right? So DLL is to Windows, shared object is to Linux. So every dynamically linked program will contain a very small statically linked function when the process starts. So this function, its job is to essentially be a part of the code, and when it is invoked, map the linked library into memory. And of course, the linked libraries are searched dynamically whenever there is a need. So this is where the LD library path environment variable comes handy. In the sense, this gives the location in which the system is going to search and which libraries a program is finding or a shell is finding. The LDD command will tell you. So the linked library that has been linked, it determines the dynamic libraries that are required by a process and which variables and which functions are needed. It maps, takes the code of these libraries, maps them into the middle portion of the virtual memory, the memory map, which is stored in virtual memory. Furthermore, what it does is that all the symbols that have been referenced within the library, so they could be variables or functions. So when the program is combined, essentially the symbols don't have a value, they point to some redirect location. But then what happens is that all of this is resolved once the library is loaded. So the functions start pointing to the right locations. So we have already seen a mechanism how. And shared libraries are compiled with the position independent code or the pick option in GCC, such that that's the way that GCC can generate code. And then once a shared library is generated, it can then be distributed all over the world, right, to every single machine. Now let's discuss the file system of Linux. So in this chapter, we'll discuss the file system of Linux, and in the next chapter, we'll discuss the file system of Windows 10. There are a lot of similarities. Wherever there are differences, I'll point it out. But Linux has kind of a, so Windows, the file system looks more like a nicely designed tree. In Linux, it's things are slightly different. So this also gives Linux some degree of beauty. And Unix file systems are also very similar. So in fact, the semantics of a Linux file system as well as its design is very, very, very similar to Unix. So the idea is basically the same that at the kernel level, we have a virtual file system. And then the virtual file system's job is to present a file system to the application where the application doesn't really care about the actual details or the implementation of the file system. And the real file system is below the virtual file system, where, of course, the file systems could be different. For example, if it's a CD-ROM, it could be CDFS. If it's a USB drive, it could be USBFS. If it's a hard drive, well, we have a lot of options. We have ext3, we have ext4, we have ZFS, which is a journaling file system. And then, of course, we have networked file systems such as NFS and AFS, where the blocks physically reside on a different machine on the network. So, for all of them, Linux abstracts it out and provides a common layer known as VFS or the virtual file system, such that user applications don't really have to care about the physical locations of the files. So it's designed around object oriented principles of basically hiding and abstraction and so on. So the VFS design exposes file objects to applications. So a file object that is exposed would look something like this. We will have the inode object. So every file will have an inode. So the job of the inode is to basically create a mapping between the blocks of the file and where exactly it is stored on a device. There will be a file object which will represent the file itself, right? So every file, uh, sorry, the file object will represent an open file. So there is a system-wide open file table, as well as what we have seen, there is a process-wide open file table. So here again, for any process, it will access open files with an integer ID. But again, the open file table actually contains a pointer to a data structure, which has a lot of information about the open file. So the inode, as I said, is more about the way that the file is stored. So this is all about storage, the way that the file is stored in the underlying device. The file object is more for open files. So it maintains the state of a file which has been opened by some process. Then for the entire file system, we have a super block, which has the data or the metadata of the entire file system. And directories are treated in a different manner, even though directories are still internally looked at as files. They have a D entry object which represents an individual directory entry, right? An individual entry in a directory is represented by this object known as a D entry. So to summarize, these are the four kinds of objects that find themselves to be the most popular in a Linux based file system. So let's look at some of the the key file object operations. So you can go to user include linux fs.h. So user include linux has most of the the functions that the kernel exports. So fs.h is basically for the file system. So for example, the operations on the file system are like this. We have the open operation. So the open operation is to open a file, and the value that is returned indicates the status of what happened. Was the file successfully opened or not? Then we either read from a file or we write to a file. So if we read from a file, we have the read operation. If we write to a file, we have the write operation. Right? And sist essentially returns the number of bytes that were successfully read or written respectively. Int mmap refers to the memory map of a file. And basically, not memory map of a file, it basically asks the operating system to memory map a file, which basically means take a file, pick out a region of the file, and map it to a region of virtual memory. Such that if a write is made to this region, well, the write number one is fast. And number two, another process will persist it into the file. Similarly, if there is a read, then we can, so first time it is being read, the data will come from the file itself, but subsequently it will be served from virtual memory. So this region kind of acts like a cache for the file, but this is way, way faster. So many times different processes map this region of virtual memory to their own address spaces and achieve a degree of a very fast method of inter-process communication. So in Linux, the ext group of file systems are the most common. ext2, 3, now ext4 is the latest. This is a standard disk file system for Linux which uses a mechanism which is quite similar to BSD Unix. So the main aim of a file system is to number one, let's write it down, organize the files and directories. Then it is basically to take a file and store its blocks on the storage device. So let me just write hard disk here, where the hard disk will basically mean any storage device. So it could be hard disk, it could be a flash drive, it could be a hard disk on another machine on the network. So that doesn't matter. What matters is that we need to have a mapping between the blocks of the file and blocks on the storage device, right? So basically address here and the address there. And furthermore, we need to organize the file system in terms of files and directories. So Linux distributions come with a bunch of file systems. So we can always instantiate a file system and we can mount it at some point of the existing file system, which starts for historical reasons in slash. So slash is a root directory in a Linux system. So we have already discussed the way that mounting and so on works in the file system chapter. So we have also looked at inodes to some extent, but now we are putting it in the perspective of Linux, how inodes are a critical part of the file systems that Linux uses internally. So the main differences, let's say, between ext2fs, which is an early version of ext, and other file systems roughly in the same category, such as the fast file system, are like this. So in general, in earlier file systems, the disk used to be allocated to files in blocks of 8 kilobytes, where the blocks themselves were subdivided into fragments of 1 kilobyte, right? To ensure that we can store smaller files without a lot of internal fragmentation. On the other hand, ext3 does not use fragments. The default block size in ext3 can be configured. It can also vary based on the size of the file. So all the ext file systems support 1, 2, 4, and 8 kilobyte blocks, right? So this of course is a configurable parameter, but of course it is important to configure this on the basis of the size of the file and the distribution of sizes of files in the file system. The allocation policy, as we have seen earlier, is a cluster allocation policy where logically adjacent blocks of a file where you would expect spatial locality in accesses as far as possible are placed in physically adjacent blocks on a disk, so that if you submit an IO request for several disk blocks, you can all retrieve them together, right? So you're essentially minimizing the I mean, you're minimizing the disk access time. Furthermore, another thing that the file systems do is that they maintain a bitmap of free blocks in a group of blocks, such that it is quite easy to make an allocation just in case we need to allocate a new block for a file. We can very quickly search for a free block and make an allocation. And sometimes we can cache this structure itself in the sense, for let's say for a given file, instead of getting one free block, we can get 8 free blocks at a time and just give it to the file, or just keep it in some sort of a cache or a pool where if later on a block is required, we can quickly retrieve it from the pool. So the ext2 file system has two kinds of file block allocation methods. The first is that we take these scattered free blocks which are scattered, which may be scattered all over the place, and then we link them, right? The other is that we take a group of contiguous free blocks and then we kind of allocate the entire group to a file. So the first one makes better use of the blocks in the sense that even if blocks are kind of spaced wide apart, then they all can be given to a file. But the second approach clearly has better performance. The reason being that they are all co-located on the disk. Hence, reading and writing to them is much faster, right? So this follows from the way that a disk is actually designed, right? So if you would go back to that chapter, so you will realize that if they are contiguous on the physical storage drive, it's much faster to access them. So another key trick that we have been seeing is the idea of journaling, which came in the ext3 version of the file system, where the updates to a file system are first written to a log file atomically as transactions. So once they are placed in the log file, they are considered to be committed. And placing something in a log file is fast because a log file is often kept in memory or it is kept in a very fast part of the disk. So over time, the log file transactions are replayed in the sense they are sent from the file system to the file system on the disk to persist the changes. So what can happen is that given the fact that these are small updates, this is much easier to do that. And particularly if there is a system crash, it is very well possible that some file system transactions may be in the journal, which is the small log that we maintain, but not yet persisted to the file system. So the key word over here is persisting, which means writing them to the permanent file system. They are not yet persisted. So, but then here again, we need to look at different methods to store a version of the log. So it's very common that the log is kept in some part of non-volatile memory or something, which kind of remains alive for a long time even after the system has shut down or crashed. So every time a file system recovers, if we still can get access to the log or we can reconstruct the log, then the actions or the transactions need to be persisted, and this has to be completed once the system recovers. After a crash, nothing else is needed. So what used to happen earlier is that the moment we had a lot of requests all going to the file system, and let's say we were processing multiple requests at the same time, what used to happen is that we used to generate a lot of transient internal state and that too on the disk. And because of that, the moment there was a problem, it was not possible to fix. In this case, we separate the logging of updates and the file system data structures. The logging of updates is nicely kept in a journal as a linked list. And then what we do is we just pick out one of these entries and we apply it on the file system. So given that the logs are typically maintained in faster hardware, the system throughput does not suffer. And given the fact that we apply them one after the other, let's say at this point if the system crashes, the moment the system recovers, we'll go back to the log, assuming there is a way of retrieving it, and look at the last operation in the log and see if that was done correctly. If that was done correctly, we'll start from there and quickly drain out the log and resume the system. So the other thing is that in terms of performance, what can happen is that we can turn random IO into sequential IO, where what happens is because of the way that a hard disk is designed, if we have random addresses, then the performance of the hard disk suffers. The reason it suffers is because our seek time and rotational delay will be very high. In the sense, we write to one address and then we immediately write to another address, which is very different. So in that case, the head of the hard disk has to seek and go to the new track and then be on the right sector and so on. So that delays things. It's a much better idea. It's a much better idea to actually reorder all the transactions such that we can make them as sequential as possible and then apply them to the hard disk. So this will also improve the hard disk performance substantially because we will wait less time in seeking the track and the sector. So our seek time and our rotational delay will decrease. So Linux does implement a couple of specialized file systems. So one of them is the Proc file system. So it is not a traditional file system in the sense that it does not store data. But what happens is that its contents are computed based on the status of the system. So, for example, let's say the kernel wants to communicate something to the user, then it will just write it to the proc file system. And many times for the user, these are read only files. For example, there is this file slash proc CPU info, or there is this file slash proc slash mem info. The job of these files is to actually provide information regarding the currently running CPUs, their frequencies, their configurations, and so on. And the same for memory. So the proc file system provides a bunch of statistics about memories, slabs, buddies, their usage, the number of threads, and everything. So this you can think of it as one, it's kind of a bulletin board for the kernel, where the kernel just puts out information which all user processes can read. So here again, the proc file system over here is like a directory because it contains all of these special files. Furthermore, for each of the files, there is a unique inode number because everything in Linux is a file, including these special files of the proc file system. So they have an inode number and they are internally stored or referenced to in the file system. So the inode number is not really pointing to a real file in this case, but it is pointing to a kernel operation that needs to generate the contents of the file. And then, of course, we can open this as a regular file and read it. So when a user tries to read, let's say this file slash proc slash CPU info to know about CPUs, what it does is it searches for this file, right? And then what it gets is the inode number. And then it tries to read the contents of the inode. So when it reads the contents of the inode, it basically is directed to the kernel, which generates all the data that is required. So it's the job of the proc module within the kernel to collect the appropriate information, put it in nicely readable text form, and place it in the requesting process's read buffer, right? So one strength of Linux is that even though this is a special mechanism and the same thing could have been done with other IPC mechanisms, including traditional system calls, message queues, and so on, we still nonetheless use the proc file system just to have a degree of compatibility with other mechanisms where everything is a file abstraction holds. It is just that when we access these files, instead of going to the regular file system, it goes to procfs, the proc file system, where dedicated kernel modules will generate the data for, let's say, proc CPU info and put it here. And we can read this with a text editor like Vim, right, with the VI editor. So let me write the crucial abstraction in Linux, which is that everything is a file. Now let's come to input output. So we have already talked about the device caches, which cache data for devices. So we talked about them in the context of page caches and virtual memory and so on. So just go back to the previous lecture. So the page cache is unified with the virtual memory system. It's a part of it. And this stores data primarily for the hard disk. On the other hand, we could also have other metadata caches which are cached in a buffer cache, which is different from the page cache, and it is indexed by the physical disk block. So what can happen is that, let's say, for parts of IO devices, like the disk is an IO device, but let's say for parts of it, we can index them by the address of the disk block, and we can get some information about in those few blocks. So this is stored in a separate cache, which is known as a buffer cache, which can, for example, tell us how much this block has been used, or whether it is expected to suffer from a failure or not, or whether it has failed. So all of this information is there in a buffer cache, as opposed to the data serving cache, which is the page cache. So Linux has traditionally looked at different kinds of devices. So every device, mind you, has a caching module. So the caching and the device are kind of kept as independent as possible, such that we can create a standardized cache for almost all kinds of devices. So Linux defines a device to also be a file, and they are all stored in the /dev directory, where you will find entries like SDA1 and HDA1 and so on. So these are all in the hard disk devices. You'll find similar entries for USB devices and so on. So internally, Linux would characterize them into three types: block devices, which allow random access to fixed size blocks of data. So block devices such as hard drives, for instance, will allow random accesses to fixed size blocks of data. So they could be either a single sector or a bunch of sectors. So recall that we have been calling a bunch of sectors a cluster. The other is devices such as character devices such as the mouse and keyboard. So instead of a block of data, they primarily return a single byte or a few bytes. And even audio devices would fall under character devices because they don't really consume blocks of data, but this would again depend on the specific type of audio device. So character devices are simple in the sense most of the time we read or write a single character from them. So they clearly don't need the support or functionality of regular files. But nonetheless, all devices are treated as files. Then we have network devices, which interface into the kernel's networking subsystem, which in itself is a very large subsystem. So coming to block devices, uh, most of the storage devices and disk devices are predominantly block devices. Block devices have a page cache for their data, and they have a block buffer cache, which serves two main purposes: purpose 1 and 2. Purpose 1 is that when we are, let's say, doing active IO and we need buffers to place data which will be written into the disk later, we can maintain a pool of buffers, and the moment we need a buffer, we just fetch one from the pool. So the block buffer cache in this case maintains this pool of buffers, which processes can use to populate data, and this buffer will later be written to the disk. Furthermore, if let's say we have completed an IO or we have read something, again buffers can be used from this pool for uh, writing data from the disk. Sorry, reading data from the disk. In addition, assume that we want to write to the disk, and there is data in this buffer pool which is yet to be persisted to the hard drive. But then a read comes, so then the read will not go to the hard drive because that will be incorrect. It will look at the latest address. I'm sorry, the earliest. I stand corrected. Sorry. It'll be the latest address, latest write to the same address in this pool. And the moment we find that request, that will provide the data to the read, and the read can then return. We will have a dedicated request manager whose job is to manage the reading and writing of buffer contents in the block device driver. And furthermore, we need a notion of queuing. Assume that there are multiple processes that would like to access the hard disk. then we would need to create a queue. So Linux, ever since kernel 2.6, has had the completely fair queuing algorithm, which is now the default scheduler for Linux. So what we have seen in the hard disk chapter is that we have looked at the elevator algorithm, where we keep processing requests from the center till the last track of the chip, and again from the track towards the center. It's like the way an elevator works, outwards and inward. But the CFQ algorithm is different from elevator algorithms. So it maintains a set of lists. Typically, we have one list for one process. It uses a version of the scan algorithm, which we have already discussed, the C scan algorithm. So the key, so you can go back to the discussion on hard disk to find out what the C scan algorithm was all about. So let me clear the clutter and explain. So the idea was that, let's say if this is the hard disk, so we go from the first to the last request. So the head basically goes from the first request to the last request, wherever it is, and then immediately comes back to the beginning without servicing any other requests. So otherwise, what would happen is, because we have, more, uh, because we have more data towards the rim of the disk, most of the time would be spent there, and the data which is closer to the spindle will get ignored. So this aspect is taken care of in the C-scan algorithm. So of course, if there are multiple processes who all have different blocks to be read or written, then we consider essentially a block of blocks or a block of sectors from each process at once. And typically, if we have n processes and we take 4 blocks from each process, then in one round of the algorithm, it will process 4n requests. That's the idea. So the structure of a device driver for block devices is like this: that we have an overall IO scheduler, which again manages the block device drivers as well as the SCSI devices. So SCSI, as I said, is a hard disk protocol, right? So we can either have SCSI or SATA, right? So this, for the special SCSI devices, there is a SCSI driver which talks the SCSI language. And so this is the low level aspect of this. At the high level, every block device is represented as a file, and we can also query this file and also modify something. In some cases, so modifying something in a device file basically means we are changing its parameters. And then, of course, we have the file system, which is at the very top. For a user application, it can also look at character device files, in the sense that reading a file sometimes may be tantamount to reading the next character that the keyboard is uh, sending to the CPU. So this of course depends on the type of the device file and the type of the device driver. So then the terminal, the shell that we see which is embedded within the terminal, that interfaces heavily with the character devices, notably the keyboard. And furthermore, on the other end, if you are using the terminal to, let's say, make a network connection or something, on the other side it will talk to the network sockets and the protocol drivers, and of course the network device drivers. So pretty much what we see is that, the same program, let's say a terminal and a shell within the terminal, these group of processes can be talking to block devices, character devices, and network devices all at the same time. So character devices are quite special in the sense they deal with data in terms of bytes and not in terms of big block. So it typically does not offer us access to random addresses the way a disk does, because in a keyboard, nothing, random addressing doesn't make sense. So the device driver registers a set of functions which implement the IO operations. So in the case of a keyboard device, it would basically be give me the next key that was pressed. So any file that is read or that is a read or write request to a character device requires very, very little processing by the kernel. In the sense that, let's say, we have a device where you're sending a single character. Maybe it could also be the keyboard sending something to a process, or maybe the process sending something to the keyboard. Like, sometimes we click something on the process, and in the modern keyboards, it's possible to turn on some lights. In that case, given it's only 1 byte, the kernel doesn't take a look at it, and it directly passes it to the device via the driver. Of course, for some subset of character device drivers which are associated with these terminals, there the kernel maintains a standard interface primarily because we issue a lot of commands for process control, right? Control C, Control D, and so on. So that is where they need to catch this, and then they need to make system calls. So then there is a higher level connotation. For example, Control C in Linux would essentially terminate the existing process, right? So in that case, this combination does hold special value. Similarly, Control Z suspends a process, so such events are caught, converted to system calls, and sent to the kernel. So line discipline is basically an interpreter for the information that is received from a terminal device. So you would see many of these processes if you run the ps command in Linux, particularly ps-ef, which will show you the processes in the entire system. So what these terminal processes do is that they accept input from the user or provide input to the user in the sense that they liaise with standard processes. They implement what is known as the standard input of a process or the standard output of a process. In a sense that when you do a printf or you write something, where does it go? It goes to the terminal or the error, right? Standard error. If there is some error, messages are written over there. So the TTY processes are important, and that is why it is necessary for the kernel to optimize this path, because many processes may be running simultaneously at the same time. So what is known as a TTY line discipline is essentially responsible for attaching and detaching the terminals to the processes, right? As and when they are connected by the user. So this basically happens by a variety of mechanisms, but many of them use a pipe kind of mechanism because the terminal is a separate process, right? And the user process is separate, but you want anything that is written to directly go here. So if you think about std out, it presents itself as a special file, which in a sense is by default opened by the process. So when the process writes something internally, you look up the file descriptor std out in the file table. So every process has three files which are opened by default. They are std in, std out, and std air. So std out is, it'll always be there in the file table of the process. So by default, the handler for the terminal is registered as std out. So the moment the processor writes something via its internal open file table, the output goes to the terminal via the std out mechanism, and the terminal then accepts it. So of course it's not a regular file, but the terminal presents itself as a file. Where of course the process assumes it's a file, but the kernel in a sense converts the call from a file to actually a message that is sent to the terminal process to display it on screen. There are, of course, other line disciplines that use a similar trick, but the terminal, of course, is special. So basically, these are not IO to user processes, but then again, networking protocols. These are again not used very commonly these days, but they used to be quite common when we had telephone based modems. They used a similar mechanism to connect processes basically for the purpose of IO. But this mechanism, STD in, out, and is quite important from the point of view of Linux design. So inter-process communication, this is a necessary part of any operating system. Linux has a lot of it. So it has a lot of support for signal handling. So there are a limited number of signals to carry information, and also processes can register their signal handlers with the kernel. Not all of them, in a sense, some serious signals for terminating a process and so on still have to be terminated, but more of the common signals. Then, of course, we can have you can communicate with the kernel for scheduling, CPU affinity, and also for regular synchronization. And Linux implements all the Unix synchronization mechanisms, such as semaphores and locks and so on. And along with that, it also supports the POSIX pthreads library, which has even more elaborate synchronization structures. So to pass data between processes, we have already looked at the pipe mechanism. So the pipe, an unnamed pipe, is typically used between a child and a parent, particularly after a fork call. So that is when we use an unnamed pipe. Also, as we have said, shared memory, and either shared memory based on a shared memory segment or on the basis of memory mapping. This is used, and this is used to a large extent. And furthermore, to obtain synchronization, shared memory is used in conjunction with other IPC mechanisms, because shared memory, on its own cannot provide synchronization. So, as we have seen, an algorithm like the Peterson's lock algorithm has to be implemented. Networking, again, it's very important to Linux. All protocols are supported. Many protocols which are native to non-Unix operating systems for PC networks and Apple Talk, they are also supported. Internally, the networking stack in Linux has three layers. It has the basic socket interface. So the socket interface allows a process to communicate or to establish connections with remote machines, right, with a given IP and port combination. Then there are protocol drivers for specific protocols like HTTP, FTP, and so on. And then, of course, there are device drivers for different networking cards, wired cards, wireless cards, and so on. So you can think of this as the MAC layer, protocol drivers as more as drivers from layers 4 to 7, and the socket interface for the IP layer, but IP and TCP, I was at 3 and 4. So the Internet Protocol Suite is undoubtedly the most important of all. So it implements routing. Along with that, it implements other protocols in layer 4, such as UDP, TCP, and the ICMP protocols for management. In addition, Linux boxes themselves can work as full-fledged network devices. So they can work as firewall management devices, have rules for firewalls, which is basically to block a certain set of addresses or a certain set of ports or protocols. Security. So Linux's security is quite elaborate. Along with that, it is possible to have additional security by these pluggable authentication modules, or PAM. So PAM is a shared library which any system component can incorporate or can liaise with to authenticate users, in the sense that the traditional password based authentication, where /etc password stores all the usernames and pointers to hashed forms of the password, that need not be the only mechanism. So network based login and so on can also be enabled. So PAM is the basic mechanism to enable that. In addition, the standard Unix based security of user IDs, group IDs, and the protection masks of read, write, execute, which we have studied earlier, all of them are supported in totality in Linux. So continuing, Linux augments the standard Unix set UID mechanism, which basically means that even if a process is owned by me, while executing, it can take on the execute permissions of another user who may have additional permissions such that the program can do more. And Linux also provides a mechanism that allows a client to selectively pass access privileges of a single file to some other process, which as we were discussing in the set UID mechanism, without giving it all privileges. So this brings us to an end of the Linux chapter, which is chapter 20. So in chapter 21 we will talk about Windows 10.